Simple interest versus compound interest, and a recursion introduction. Okay, so we're going to compare simple interest to compound interest. I've done an examples here, and you can see the similarities and the differences. So I'm going to highlight they both start with the same starting point. So you can see we've got this lovely line here. And so they're all starting at the same point. But simple interest is a line, and I can show you that because I can draw a nice line like this. And you can then realize that y equals a plus bx. That kind of maths that you've done before does apply to this because that is a line. But if I try and draw a straight line on this one, you can see it doesn't quite work. There's actually a curve going on like this. And that's the interesting thing about compound interest. Compound interest always wins eventually, okay? So you can imagine you've got a graph like this, and you've got your dollars here, and then you've got your time here. If we said like simple interest is a lovely straight line, let's do a lovely straight line like that. This is your simple interest, but doesn't matter how low you start. So we could have a very low interest rate, but eventually it'll curve up into an exponential for compound interest. So there'll always be a magical time here. I don't know what that time is. I'm going to call it mystery X, where compound interest will win. Before this magical point, simple interest is winning. But after that point, compound interest wins, and it will continue to win forever. And it doesn't matter how low you start with a compound interest or how high you start with a simple interest, there will always be a point in the future where compound interest will win. So you might say, oh, simple interest of 50%, that's amazing. And compound interest of 0.5%, that's terrible. But believe it or not, in enough time, that 0.5 compound interest will end up being more than the simple interest at 50%. Okay, we're going to start with simple interest because it's simple. Here's our money increasing this way. Here's our time increasing that way. And you can see now that we've got two parts to this. And so we've got the blue part and the green part. And I'm just going to show you like a bit of a line here to distinguish between these two things. So this is actually 10,000 here. We can see the 10,000. This is actually the point for V0. This is V0, V1, V2, V3, V4, V5, and that makes sense. So this blue part represents V0. The important thing to note is that blue part's not changing. So this is also V0, and that's V0, and they're all got that blue part, which is V0. And above it, the green part is the amount of interest. Now, what is interesting is what you've got here is this is our V0, and we're going to V1, right? We've had to increase by this amount D. So to get from there to there, we have to plus D. And then to get to V2, we have to add another D. Can you see we've added another D there? All these D's are the same size. Just believe me, sorry about the wonky drawing. So to get to V3, we have to add a D. There it is. So we've added a D. And then we add another D to get to V4. There it is there. And then we've had to add another D to get to V5. And that's it, adding there. So we're always adding the same amount. We're always adding D. And that D stands for difference. So you can say D equals the difference. And so when we're looking at this so far, what information have we got? We've got that V0 equals 10,000. And we're going to put a dollar sign because it's financial maths. So we'll put a dollar sign. And then we've got this D, and the D in this case, the D, I'm just going to tell you what the D is. I'm going to do a calculation for the moment. D equals $1,200. Let's make that look like a bit of D. All right. So we can say like, okay, V0 is 10,000 and V1 is V0 plus the D. So V1 equals V0 plus D. So that equals, say, 10,000 plus the 1,200. And so that equals 11,200. And don't forget the dollar sign. And we're going to, well, what was V2 equal? Well, V2 is the V1 plus another D. So it's V1 plus D. equals, so that equals 11,200 plus the 1,200, and that equals, if I'm getting this right, $12,400. And we could keep going like that forever. And that's basically what we want to be able to say is, okay, so the next term, and we're going to say like, so Vn plus 1 is the next term. What does that mean? Next term. So V1 was the next term after V0. So we can just write a recurrence relationship. Now, recurrence relationship has two parts. We've got to say, we got our V0. We can say the Vn plus 1 is the term before Vn plus the d. That's all we did each time, right? And so that's a rule right there. That's something really important to remember. And so our recurrence relationship, we've got to combine two parts. So I'm going to do it over on the side here. So we've already done V0 equals 10,000, and we're going to do a comma, and then we're going to say, well, Vn plus 1 equals Vn, and what was our difference? 1,200, so it's plus 1,200. And this part, so this part here, that's the rule. And all of this together is the recurrence relationship. And that's what you've got to do each time with a recurrence relationship for simple interest. We're just adding each time a constant amount. So that's a constant amount d. Okay, to summarize everything we got from before, we know the initial term, called the starting point, is V0, and in this case, V0 was 10,000. And we put a comma, don't forget to put the comma, very important. And then we say the next term, Vn plus 1, equals Vn plus d. In this case, the d is 1,200 and d is for the difference. So the Vn plus 1 equals Vn plus d, that's the rule, and the initial term plus the rule makes the recurrence relation. So whenever they say, give me the recurrence relation, they want you to give us an initial term and a rule and stick them together with a comma in between. Okay, now this is great, but if I want to work out what V5 is, I've got to start at V0 and then work out V1 and then work out V2, etc. So I might be starting here at V0, and then I can work out from V0 V1, and then from V1 get V2, and then from V2 get V3, and then from V3 get V4, and then from V4 get V5. And that seems like a lot of work to get to V5. Isn't there a way to shortcut this? Well, there actually is, because remember, every time you're just adding a d, so it's always plus d plus d plus d to get there, right? So if you look at this, V1 has 1 lot of d, all right, and V2 has 2 lots of d, and V3 has 3 lots of d, and V4 has 4 lots of d, and V5 has 5 lots of d. Wait a minute, I can see a pattern. So if I wanted to know, say, like, V10 equals what? Well, I'll go, hang on, V10 is just going to be, well, it's going to be this amount V0, because that's constant, plus a certain amount of d, and that how much d? It's going to be 10 lots of d. So V10 would logically equal V0 plus 10 lots of d, which means it ends up being 10,000 plus 10 times 1,200. Should be straightforward to get that. That is actually 22,000. In this case, we need to put a dollar because that's the value. So you can go straight ahead to that. So you can also have, this is not a recurrence relation, this is just a straight rule. You can actually have another rule, which is that Vn equals V0 plus n lots of d. And that's another rule that you need to know. So if you think about it, at time 0, V0, that will actually work out. Like V0 equals V0 plus 0 lots of difference, and that's true. There's no d added on there, and so term 3 is just V is literally. Grab the highlighter pen. So term 3, you've got this amount of V0 plus 3 lots of d, and that makes sense. Easy peasy, lemon squeezy. Now we're going to look at compound interest, and there's a lot of things that are similar, and just one fundamental thing that's different: the interest. So we've got our dollars going up here. We've got our time going along here, same as before. We do have that blue bit and the green bit, and the blue bit is exactly the same size as before. I'll try and line up a nice line there. And so this is V naught. So this is 10,000, that's 10,000, that's 10,000. That has not changed at all. But we don't have a constant difference. We're not adding a difference. To get to the next term, to get from V naught to V1, you have to multiply by R. R is for ratio. So R is a ratio. Okay. And so let's try and do a bit of error there. To get from V1 to V2, you have to times by R. There's our V2, and then we times by R, and we get V3, and we times by R, and we get V4, and we times by R, and we get V5. So we have to multiply by this constant ratio. And as I said, like if you try and draw a straight line, hopefully this will show this. It's not that easy drawing a line on this computer screen. You can see that it's starting to accelerate. So we're starting to actually go more like this. And that's the joy of compound interest. Why people love compound interest so much is because it starts to accelerate and go up quite steeply. And so if someone owes you money, that's great. If you owe someone money, not so great. All right. So we got to set up a recurrence relationship. We can see that V naught is exactly what we had before. So V naught equals 10,000 in this case, and we do a comma, and we've actually set up the rule. The rule is that Vn plus 1 equals this ratio times the Vn. All right, and I'm just going to put that secret little time symbol in there. Just remember, whenever you put two letters next to each other, it means times, sort of thing. Now I'm going to be easy on you here. I'm going to tell you that the ratio in this case is 1.12. It's the same interest rate as I've been doing before, but you can see by compounding, it's actually accelerating. So we can actually say here that for our situation, that this equals 1.12 Vn, and so that is the recurrence relationship we have here. So this is our recurrence relationship. Okay, so just like we had before, you could have your V naught, and then you could have your Vn plus 1 equals R times Vn. In this case, our R is 1.12. Tell you how to calculate R later. I haven't told you how to calculate D either, to be honest. Now, let's have a look at some of the calculations on just finding the next term. So if we say V naught equals 10,000, that makes sense. So then V1, the next term, this is just putting n equals 0 into that term. So n plus 1, 0 plus 1 is 1. And so n is 0, so V0. So V1 equals RV naught. And so that equals 1.12 times 10,000, and that gives us it is 11,200. Now what you might be saying is actually that's exactly the same as V1 on the simple interest. So our V naught is the same and our V1 is the same. So what's the big deal? But we're building up here. So V2 equals RV1. All right. So we're going to do 1.12 times not 10,000. We're going to times by 11,200, and this equals 12,544. This is where we might actually start telling you put the 0.00. Very important point that you look at this 00, 2 decimal places. Money is always 2 decimal places. I know the 1 cent and 2 cent coins don't exist in reality, but they do exist in the virtual world of electronic computing. So your bank account still goes to 1s and 2 cents and stuff. So you may work in a shop, but that doesn't mean that the 2 cents don't exist. So you can see that's actually slightly more than what we had before. We've actually got before, if you remember, our next term for simple interest was actually 12,400. So you've actually gained $144. So you can see that's worthwhile, isn't it? And then if you did V3 equals RV2, so that's going to equal 1.12 times 12,544.00, and you'll end up with, I've got to get this right, 14,000, put a dollar symbol, $14,049.28. And again, we're starting to really accelerate away here, because before the term 3, if you don't remember, fair enough, you don't remember, you didn't read off the graph, it was only 13,600. So now we're at $14,049.28. So we're making a lot more money, and that's going to keep accelerating on and on and on. You can see this green term here, this is getting bigger and bigger. Eventually, like, the principal doesn't matter. The green will be the majority of the spike. You can see it's already quite quickly accelerating there. And that's why people love compound interest.
Okay, we're at V0, and we want to get to V1. We've got to multiply everything by R. And to get to V2, we're going to multiply everything by R. And to get to V3, we're going to multiply everything by R. And to get to V4, we're going to multiply everything by R. And when we get to V5, we're going to multiply everything by R. That's a recursive way of doing it, but that can seem like a bit of a pain. I mean, isn't there a shortcut way to get there? Well, in simple interest, we had plus D plus D plus D. We could have just said, oh, well, that's just like 3 times D, 3 lots of D. So we can see that repeated addition is just multiplication. And you can do the same thing here. So if you have times R times R times R, well, you can say, well, that's R to the power 3, or R cubed. So repeated multiplication is powers. So we can actually think if I want to get to V5 or V10, then there must be a way to get there. And we can do that. So V10, what does that equal? Well, it's going to be V10 equals R to the power 10 times our initial value V0. So that's going to equal 1.12 to the power 10 times 10,000. All that in your calculator, you should end up with, don't forget your dollar sign, $31,058.48. And as you can see, that's getting us a lot more interest than we got before. Before, with simple interest, same amount, 12%, we only got $22,000, but now we're getting $31,058.48. So it's giving us a massive, massive return. So compound interest, way better than simple interest. And we can write that as a formula. So then Vn equals R to the n times V0. And that's a useful formula also to write down.
Let's compare simple interest to compound interest. And what we can see, well, that's V0 and that's V0. And you can see that that is that blue line, and it's the same for all of them. So V0 equals 10,000 for this one. And V0, the initial term, also equals 10,000. So I've kept these two the same. But simple interest is you might hear the word arithmetic. Arithmetic? Why is it arithmetic? Because arithmetic is adding. So we're adding a D each time. So we said that the next term is the current term plus the difference, in this case, a Vn plus 1200. I set that to 12% interest. The compound interest is also at 12% interest, by the way. So this one's called a geometric sequence, because you have to work it out using geometry, apparently. So times by R, times by R, times by R, times by R. So the timesing makes it geometric. We put a comma, and we say Vn plus 1 equals this ratio times the current term. And so in this case, we said the ratio is 1.12. That's that 12% interest. We'll discuss that more, how to work that out another time. So that's 1.12 times Vn. So here is the recurrence relationship for simple interest, and here is the recurrence relationship for compound interest. So we can call that the recurrence relation. Okay. But we also said, look, sometimes I want to work out V20 without having to work out V1, 2, 3, 4, 5, all the way up to 20. So we can actually say here that the Vn also equals V0 plus n lots of D. That's a nice sort of rule that just shoots us ahead. I like to call it the shoot ahead rule. And then this one was the Vn equals r to the n v naught. And that's the same sort of thing, but that's a rule that takes us straight to, if we want just term 20, you just say n equals 20, boom, put them in, and we get a value for 20. So that's the two things side by side, looking at it in the way of a recursion relationship. And in the next video, I'll actually try and explain all this, but change all the terminology just to annoy you and start talking about it in a financial sense with interest and principles and stuff.